Good morning. We will have a midterm next Tuesday, so coming rapidly. And if you have any questions, both today and Thursday lecture time will be a good time to ask. Specifically Thursday, we'll dedicate most of the time to answer your questions. I have posted practice homework, 2 sample midterm exams. All of those are for you to practice. You don't have to turn it in. I will post the solutions on Wednesday evening or sometime during Wednesday. So try to work out the problem before reading the solutions and bring your questions either to GSI's office hour, my office hour, or the lectures on Thursday. Okay. Any questions to start with? Anybody have any questions? So closed book, 2-page cheat sheets, whatever density you want to write. The only limit is letter size paper, single side, double side, high density printing, handwriting, whatever you want to do is fine. No computer, calculator is required. So I'll send another email reminder, but you'll need a calculator. Okay, so I'll finish the diet discussion, the small signal, whoops. Let me fix. Okay. All right. So small signal model. This is something quite a few of you have questions after the last lecture. So let me kind of go over a more detailed, more general view, what the general small signal model means. So if we take a simple circuit like this one, it's a diode circuit connected with R. We have solved this circuit before. So we previously we solved this circuit by iteration, okay? And so assuming we know the DC solution, so this is known as a DC solution, okay? So assuming we have solved that, which means ID, the DC current, is equal to exponential, sorry, there is an IS, so exponential VD over VT. Okay, there's a -1 that is so small that it can be neglected. So we solve this equation as well as the equation that VS, the source energy is VS is equal to ID times R plus VD. So you solve these two equations, you will obtain a set of solutions. So we have done that previously. Now, if we add a small signal on top of a DC power supply, which is represented by a battery here, the voltage across the diode is going to deviate from the DC value by a small value here. Okay, so here is a notation that the circuit community often use, and this is a convention that we will stick to in this course as well. So for example, we write VD is equal to V, capital D, plus VD. So all cases matter here. the small letter, capital subscript means total signal. Okay, so this is not arbitrary. Okay, and if so, these are capital symbol. Okay, capital symbol, and sorry, small case symbol. And capital subscript. So just to note that they are all different. And if both of them are capital, this is DC. Usually it's reserved for bias, okay? So these are like 3-volt battery that you apply, or the voltage drop across the diode. When you solve the equation, it's 0.72 volt, for example. And the small case, both are small case. This is AC small signal. Okay, usually it's implied it's at some AC frequency, so it's oscillating. Okay, so this is oscillating, and the amplitude VD is usually much smaller than the DC value VD. So that's the convention here. So you see now, I put down in the DC case, there is a battery, steady state battery, VS. It results in a solution capital V, capital D. Now I add a small signal, V sub S. This will result in a corresponding change in V sub D, both small cases. Okay. So the small signal solution basically is a more systematic way of solving this. And we solve this by looking at basically this solution. We start with one of the solutions. So we look at this diode element here. So we say, well, now ID plus ID. Let me start with, so ID, total signal, is equal to IS. IS is constant, doesn't change. E VD over VT, okay? Again, ignoring -1. And now noting that ID consists of 2 components, the DC component and the small signal AC component. Likewise, VD consists of VD plus VD. Have to be paying real attention to all the subscripts, okay? So if we substitute this into this equation, then you'll get ID plus ID is equal to IS exponential V, sorry, this will be capital V D plus small v small d divided by VT. Okay, so this is a new solution. When I superimpose this small signal, we can solve this equation just like the iteration we solved that previous equation. To save us time, we can utilize basically a Taylor expansion. Okay, so we will do the following way. We'll make this as IS. So if you think of this as a function of this as a if you think of this as a function, this is a function of VD plus VD, and we can use Taylor expansion, do FVD plus DF dV times VD. This is small signal. Okay. So this is what we will do here. So this is equal to IS E VD over VT plus, now we take a derivative of the whole function, right? So This is IS, constant stays. And the exponential function, you take a derivative, is 1 over Vt. And you evaluate this function, V at the Vd. So this is equal to basically exponential Vd over Vt. So this is the dFdV term, right? And times the small signal term, Vd. So this is think of this as like a delta V. So this is a small signal term, right? So now you'll find that comparing the left side with the right side, this ID is exactly equal to this value, the bias value for the Taylor expansion. So you can quickly equate the small signal ID, okay, is equal to, now we noted this expression here, this IS times this exponential term is exactly equal to ID, right? So this is equal to ID divided by VT times VD, okay? So we can think of this as basically VD divided by ID is equal to VT divided by ID. And previously we gave a name to this. This is called RD. So RD is small signal equivalent resistance or small signal resistance. So there's kind of two ways to look at this. Previously, we look at it purely from the circuit point of view. Today, we look at it purely from mathematical point of view. It's just a Taylor expansion. So when we say we solve the circuit by two steps, first, solve the DC problem. Next, replace all the DC element with AC element. So that's what we mean. So to solve a real circuit problem, this is the two-step process. So we follow typically this two-step process to solve the problem. So first problem, solve the DC problem, okay? So DC problem, this will be a battery, right? And R and the diode, okay? And so this is Vs, this is R, here voltage drop is Vd, and this is the iterative solution. So for example, we find the solution to be, for example, Vd is equal to 0.7252 volts, ID is equal to, say, 1 milliamp, for example. This depends on the resistor value, of course. So the second, we replace circuit with all small signal equivalent circuit. When we do that, we have to do a few things. First, all current, you learned this in 16A, so all DC voltage source will be replaced by short circuit, okay? And all DC current source will be replaced by open circuit, okay? This is because ideal DC source fundamentally have zero impedance. A battery, for example, or your power supply, when you add a function generator in series, that power supply voltage is not changing. It's not responding to your function generator voltage change, okay? So, and then replace for example, in this case, we only talk about diode, but later on we'll talk about transistors. We'll be doing the same thing with the transistor. So replace diode with RD. Okay, so this circuit will become, we still have AC current source left, right? And we have R does not change. It's a linear element. AC, DC is all the same. But diode is nonlinear. Now we have a linear equivalent circuit, that's RD, all right? And this is now small v, small s here, okay? And if we are looking for what is a small v out here, and now this is a simple voltage divider, you can write it very simply as R plus RD and RD times Vs. So once you linearize it, and RD is of course equal to VT, thermal voltage, divided by the DC bias current of the diode. Okay. So it becomes a very easy solution to deal with the AC signal. The bias, you solve it once, and then you can do many things with the AC circuit using this approach. Okay, any questions? I gave you a practice homework problem, okay? The homework problem is something like you apply a voltage, you bias a diode with current source, okay? And I believe there is RS, there's a coupling capacitor, there's a coupling capacitor here, right? And you apply, for example, a Vs here. And here is power supply voltage. We typically call VDD. The name will become apparent later. And for example, if this is the V out, okay, so you can practice the previous rules and first transforming this into AC equivalent circuit. This particular circuit is kind of trivial DC-wise. We are biased with a current source, ID. So there's no need to solve DC problem. DC problem is trivial. Diode current is ID, and you can simply write the small signal equivalent circuit. Here, it has a coupling capacitor, okay? Coupling capacitor, which you use already in your lab. Coupling capacitor, basically, you think of it as the complex impedance, ZC is equal to J omega C. And usually coupling capacitor C is very large, okay? So when C is very large, this is usually much smaller compared with all other resistance, compared with all resistance of interest. So in other words, we treat it as short circuit. Okay, coupling capacitor is a short circuit. So this equivalent circuit becomes really simple now. We have AC source. We have this source resistance, I guess is RS here. RS, that's the same. Current source become open. Diode become RD, right? And coupling capacitor become all short circuit. So this become VD. It's the same circuit as we have just analyzed. It's simply a voltage divider. So VD is basically equal to V. So VD is equal to Vs times Rs plus Rd, and voltage drop is on Rd. So it's simple voltage divider. These are relatively simple examples. As we go to more complex example using transistor, replacing transistor with small signal circuits, then you will need to utilize your skills in KCL, KVL circuit analysis. That's one thing at the end of this course. you should be very good at. That is, if I got a complaint from the next course instructor of 140, say, what do you wish the students all know? Well, they wish the students all know how to do this circuit analysis easily. Okay, so that's completion of the small circuit element discussion. Any questions here? Okay, yep.
So why is ID only, so VDD does not affect this circuit here?
VDD is a DC power supply. So the one of the circuit convention, you might have seen that in your lab, when we write in this, we really mean, what we really mean is, maybe let me use a green color here. What we really mean is that this VDD is actually a battery. So it's actually connected to a battery here, okay, or a DC power source. And so here is a real loop circuit here, and this is VDD. And so VDD will replace with a short circuit. So this is short circuit, but the current source here, the current source is being replaced by an open circuit. So we basically just take out the entire branch of circuits.
So why can't we skip step 1, solving DC?
Why can we skip? So in these particular example problems, because there's only one loop and I use a current source, so it is trivial. The current is known because I bias it with a current source. If I bias it with a voltage source, then I actually don't know what is ID. Like in this example, I don't know what is ID. If you recall previously the iteration problem, how do we solve it? You still remember that? We assume the voltage drop to be 0.7 volt to start, find the current, find more accurate voltage, and do iteration. And it will become apparent when we go to transistors. If you don't solve the DC, you don't know the bias point. Okay. Before we move on to MOS, kind of the heart of this course, I like to mention kind of common use of photodiodes, common use of diode. And diode is light sensitive. When we reverse bias a diode, it's light sensitive. So this is all the cameras you have on your cell phone. Your cell phone now has, I don't know, 3 or 4 cameras. And pretty soon it may even reach 10 cameras, some very high resolution. So this is just to kind of understand, explain what is a photodiode, why it can be used to detect the photocurrent. So a diode, we still usually represent it by a symbol. It's usually reverse bias. So we usually will apply typical bias condition. We may apply with a low resistor, and we will apply reverse bias. Okay, so this is a reverse bias. And how does the IV curve change when light shines on it? Light shines on it, it will generate a current. So without getting into more detailed device physics, this is like in the reverse bias, there's no current flowing, but there's a huge field developed in the junction. So when you create an electron-hole pair, the photon knock out one electron from bound atomic bonds between silicons. So it creates one electron, one hole. Okay, so basically silicon, think of silicon lattice. And when there's a sufficient energy, when light hit, okay, and light will create knock out the electron. So bond has 2 electrons. So you create one free electron here, and leaving in here one hole. So now this electron hole, so you create light, create electron hole pair. And this electron hole pair can now conduct the current. So as a result, this generates a photocurrent. We typically represent this current by, if we want to really emphasize the photocurrent, we will put a current source here. So this will be I photocurrent here. So it's kind of in parallel with a diode. So now this photocurrent will flow through this resistor, and you can detect the voltage change in this resistor. So in IV curve, this is the normal IV. Let me redraw the IV at the bottom here at the lower voltage scale. So if you recall, we say, well, here is ID, VD, okay. I should write this as VD. And we say, well, this is the exponential behavior. So this is ID equal IS exponential VD over VT minus 1, right? So we normally operate in the first quadrant, okay, the first quadrant and the third quadrant. When voltage bias is negative, current is negative. When voltage bias is positive, current is positive. When we shine light on the photodiode, you open up the diode area as in your camera, in your cell phone, it now can respond to light. What happened to light is light will add current on top of the original diode characteristics. So the current is basically here, I photocurrent. So this is this photocurrent here. This photocurrent is proportional to light intensity, okay? If you have stronger light intensity, this current will be stronger. And what happened here, if you add a current component, and the current flows in the reverse bias direction current. So you are basically linearly shifting the IV curve. So with light, this curve will be shifting like this, all right? So it's like a uniform shift, okay? All these arrows are equal, okay? And these arrows are exactly photocurrent. If you increase your light intensity further, well, it just go shift it down further. If you have more current, it just shift it further down. So if you put the simple low resistor here, as in this case, if we put the low resistor, now we operate in the third quadrant. So photodiode mainly work in the third quadrant, okay? Third quadrant means it's a negative voltage, negative, it's a reverse bias direction. And if you have a low resistor, so if you put a low resistor, you can pick up the voltage change due to this additional current. So this example here kind of zoom out to higher current, higher voltage. You see kind of a more flat IV curve here. And with the current, you can see clearly 2 milliwatt, it drops down to nearly, not quite 1 milliamp. And 4 milliwatt is almost equal spacing. So this just goes equally here. And the sensor circuit basically try to pick up this current, amplify this current. And eventually you combine all your two-dimensional pixels, you get the picture. Yes?
I'm a little confused about the simple. Isn't that forward bias?
So when I draw, yes, you are right. I draw this opposite. This should be this. Current direction should be, let me see. So the normal diode current, let me draw this. So normal diode current is flowing from P to N. So this is a normal current, forward current. Okay. And the photocurrent is the same direction as a reverse current. So yes, I drew it the wrong way. So the IPH should be going in this direction. So if I draw equivalent current source, it should be like this. Okay, thank you for pointing this out. Another diode or very similar devices is solar cells. And solar cells work almost exactly the same way as photodiode, except we don't apply reverse bias. All the purpose of solar cell is to generate voltage. If you have to attach a battery to it, well, it sort of defeat the purpose, right? We are not, we are consuming energy from the battery. We are not generating energy. So for solar cell, basically, we operate in the fourth quadrant here. We operate mainly in this fourth quadrant here. As before, the IV curve is just a linear downshift. So this is the same as in a photodiode. When you shine current, the whole curve shifted by same amount, okay? If you don't apply any bias, you'll find out that this voltage here is called open circuit voltage. This point, current is equal to 0. So at this point, I is equal to 0, right? This is IV curve. So at the horizontal axis, current is equal to 0. So the voltage there is called open circuit voltage. So VOC is called open circuit voltage. So this means if you put a solar cell, it's literally an open circuit diode. When sunlight shines on the diode, a voltage develops at the two terminals of the diode. The polarity of the voltage is such that the P side will develop positive voltage. So this is kind of your VOC here. So the current flow is again opposite direction to not that of normal current. So you operate in the fourth quadrant, and sunlight create this area. And there are a few important parameters: the open circuit voltage, the short circuit current. So this represents the short circuit current, okay? And they define an area. They define an area here. This kind of defines the energy you can generate. If you operate here, you generate the power equal to this area here. This area basically is equal to I times V. V is the generated voltage. I is the generated current. So this is basically the energy generated. Okay, and naturally, a good solar cell, you have very large area here, and this area is called field factor. So if you normalize this square area over the entire area covered by the red curve, that ratio is called field factor. It's not important, just so that when you see the literature, you will understand what this means. So the higher the field factor, it means the generated energy is higher. Ultimately, this translates to solar cell efficiency. And typically, if you buy a solar cell, you typically get something like a 20% efficiency. Depends who you buy it from, the quality of it. But there's a theoretical limit as well. If you get the very best silicon solar cell, so the efficiency will be 31%. for silicon photovoltaic cell, PV photovoltaic cell, right? And you hear probably TV commercials. SunPower is the one that utilize single crystalline silicon PV cells, and they are delivering efficiency around 25%. Why not 31%? Well, it's really hard to reach 31%. So it's typically 20 to 25%. If you go to more favorable materials, such as gallium arsenide, you can potentially reach higher than 31%. Okay, depends on the size of the band gap and so on. So this is the topic for EE134. If you are interested, you can find out more about all these applications. But it's basically a semiconductor junction that you have already learned. Okay, so far so good. So this concludes our discussions of all diodes. So in summary, we talk about the device physics. What are they made of? What's the origin of the current? The circuit model, exponential circuit model, we derive it. How to solve the DC bias. How to solve AC circuit that has a diode in there. We talk about large signal behavior, like rectifier, converting AC voltage into DC voltage. We talked about the peak detector, negative peak detector, level shifter, and so on. So those are kind of common usage of diode. So our midterm cover stops here. If you have questions, we can go on, discuss questions. Otherwise, I will move on to start talking about MOS. Okay, let's go to MOS. So MOS stands for metal semiconductor, a metal oxide semiconductor. Okay, this M is metal, O is oxide, S is semiconductor, basically silicon most of the time. Okay, so this refers to a structure that you have a piece of silicon, okay, and you have a layer of oxide. Oxide here usually means silicon dioxide, even though in modern transistors, they are not silicon dioxide anymore. They are other fancy oxide. We'll talk a little bit about that. And here is a sandwiched layer on top. This is metal, okay. For a while, metal is really not metal, it's a doped semiconductor, but now it becomes metal again. So we go through these evolutions. And so this is known as MOS. By itself, it is a capacitor, nonlinear capacitor. If we attach more electrical connection to it, we make it into a transistor, which can be a gate or amplifier. So to start the discussion, let's review what is a capacitor. So a capacitor is basically the simplest capacitor, metal parallel plate capacitor. This is known as a linear capacitor. When you apply a voltage, you start, if you apply in the positive cycle, you start to populate it with a positive charge in one plate, negative charge in the other plate. If you attach an AC source on it, these will be oscillating. So there is a fixed amount of positive charge that are due to the DC voltage, and there will be smaller amount of charge that are sloshing back and forth corresponding to this additional AC term. The capacitance value is very well defined. It's epsilon, dielectric constant, times A, which is the area of the parallel plate, divided by D, which is spacing between the plate, as shown here. And if you plot the CV curve, capacitance versus voltage, and you look at the expression of a capacitance, well, it's not dependent on voltage. So it's basically a straight line. So this is a linear capacitor. It's a trivial case. And if you put the capacitor circuit element into your circuit, this is what you get, okay? Inside integrated circuits, usually it's much harder to make a good capacitor. Very often, we just use semiconductor MOS as a capacitor element. Okay, so now here is a nonlinear capacitor. We have learned actually already one nonlinear capacitor, that is reverse biased PN junction. Okay, so here is a brief review of a reverse biased PN junction. Now I draw the PN junction in the vertical direction, but it's a one-dimensional PN junction. Top is N-type, bottom is P-type, and if I apply a reverse bias, so positive voltage connected to the N-type, okay, and negative voltage connected to the P-type. So this is a reverse bias PN junction. The reverse bias creates a depletion width, okay, and the depletion width we learned in the previous module. It's related to the doping concentration, related to building voltage, related to the reverse bias voltage, okay? The higher the reverse bias voltage, the more the depletion width becomes, okay? So when we apply additional AC voltage source, we superimpose these two sources. This is basically same effect as a metal parallel plate capacitor. In the positive cycle, some positive voltage will appear here. The positive voltage really means, well, we are actually, think of it in the positive cycle. In the positive cycle, we are increasing depletion width a little bit more, right? If you further reverse bias it. When the reverse bias more, okay, you exposed additional layer, you pull the electron back. So what you are left here is a positive charge, okay? This positive charge, even though it comes from donors, these are ions, it's not mobile itself. The electron is mobile. So the electron is responding to your small signals. When in the negative cycle, it will come back and neutralize this donor ion. So it behaves exactly like a parallel capacitor, okay? And you know, first time you may want to think about in detail how electron actually cover these ions, but it behaves exactly like a parallel plate capacitor. And this parallel capacitor with a spacing of W. So capacitance is simply epsilon times area. This is the area in the lateral direction divided by W. But now W is a function of voltage. So this is no longer constant. So if you plot, this will be something like this, okay? This will be proportional to 1 over square root V building voltage plus the reverse bias that you apply to the diode, okay? In the forward direction, the curve will continue a little bit. However, the current starts conducting, and the current will soon overwhelm the capacitor functions. So when we need a capacitor, we never bias it in the forward direction. We always bias it in the reverse bias direction. So we don't really worry about what happened to these capacitance in the forward direction. It's still there, but it's going to be dominated by the forward current. Okay, so this is the simplest type nonlinear capacitor that you have already learned. Okay, now let's move into MOS. So metal, semiconductor, silicon, semiconductor. So this is silicon. The silicon is usually doped, okay? In this case, it's p-doped. We refer to this silicon as body. So this silicon is referred to as body. That's the terminology for MOS transistors. We refer to the entire area as a body. So now you think of it, this is almost like a PN junction. This is almost like a parallel plate. Here is a metal. Metal is a parallel plate. The diode, the insulator, well, it's kind of like air filled with a dielectric. The epsilon silicon dioxide is equal to the relative permittivity is 3.9, okay, nearly 4 times the dielectric constant of vacuum. So when you have oxide, your dielectric constant goes up by about a factor of 4. Now, semiconductor, so this is the tricky part that needs more explanation. So this is interesting part. A full transistor will have 2 additional terminals, okay, which we will discuss later. But the main capacitance is here. We are talking about 2-terminal device. One terminal is VG, the other terminal is ground. So this is a vertical one-dimensional device. This capacitance should at least encompass these capacitance across the oxide, but it should be more. It's more complicated than that. So let's look into sort of the more detail of these capacitance. So same MOS, I remove the contact for now, okay? And think about, this is a P, it's very important what this is doping type. So this is P type. For the time being, it may be helpful to think about it's like a PN junction. So think we have a PN junction, okay? So this is N type, but between PN junction, we inserted a silicon dioxide, and here we have a P. So it's a PN junction with a silicon dioxide in there. What are the impact? Well, first, let's look at reverse bias direction. Reverse bias will be applying forward bias direction. Let's think forward bias direction. Okay, forward bias direction, we will apply negative voltage. So very small, very negative voltage, since P is ground, right? So we apply negative voltage to N side. This is reverse bias. Sorry, forward bias. I'm confusing myself. So this is forward bias. Okay. What happened in the forward bias? Well, electron, there are a lot of electrons. They want to cross over to the junction, but silicon dioxide is the insulator. It stops it. They cannot cross. Hole on the P side, you have lots of holes. On forward bias, you are going to inject way more holes into N side. Again, they are stopped by the oxide. So in this case, they behave exactly like a metal plate with oxide in between. So they are constant capacitance. So when the voltage is very small, the capacitance is basically constant. So this refers to this area where VG is much, much smaller than 0. And why is constant? Well, the capacitance is basically equal to the oxide capacitance. Okay? And there's a distinctive voltage below which this voltage is like this. There's a It's called flat band voltage. It's not important for this course how to calculate flat band voltage. The flat band voltage is a voltage below which you will start to have this carrier accumulation across the interface. So there's a terminology for this region. It's called accumulation region. So we are accumulating electrons and holes. They are stopped by oxide from recombine with each other. Okay, so this is relatively straightforward. Now, after my voltage become larger than flat band voltage, so think about V eventually become greater than 0, okay? V greater than 0, then this feels like reverse bias. Right? Reverse bias, except it's again separated by oxide. But reverse bias, there's no current anyway. So the oxide is being pulled away even more. So in the reverse bias case, the depletion region developed. Okay, so there's a little bit depletion region here, right? And usually the Pn is very heavily doped. I put N++ here to indicate high doping. The P doping, so the charge will disappear here, okay? Instead, the depletion region will develop here. So this is depletion region, just like PN junction. Okay. Usually the doping, so the depletion region is inversely proportional to doping. Usually we ignore the depletion region drop in this case. So we ignore this. We just think of the bottom two side here. So now we have two capacitors. We have one capacitor that's equal to the oxide capacitor. We have a second capacitor, which is similar to the PN junction reverse bias, the capacitor. Okay. So these are exactly two capacitors in series. Okay. So on this side, we have Cox in series with a C depletion capacitor. So C depletion is a depletion capacitor. Let me write the terminology here. This is a depletion capacitor. Okay, and this is basically equal to epsilon divided by W. And Cox is the oxide capacitor. It's basically equal to epsilon SiO2 divided by T, if we use T to represent, or Tox to represent the thickness of the oxide. Usually we use OX as a symbol. So this will be epsilon OX divided by TOX. Okay. And for depletion capacitor, this epsilon should be silicon. Okay. Epsilon silicon is very large. Epsilon silicon is roughly about 10, 12 times epsilon 0. Epsilon oxide, as we mentioned earlier, is about 4 times epsilon 0. So silicon has even higher dielectric constant. Okay. Now remember, this W is voltage dependent, just like reverse bias. So it basically follows this curve here. Okay. So this curve is proportional to basically some kind of, actually, it's better to write it exact expression. So this capacitance here, for capacitance in series, it's inverse sum, right? 1 over C equal to 1 over C ox equal plus 1 over C depletion. Question? TOX is thickness, so it's here. So TOX is thickness of oxide. Okay, so capacitance becomes smaller when you put them in series. It's opposite of resistor. When you have resistors in series, the resistance value add up, so resistance becomes larger. Capacitance is the opposite. So you have all learned about capacitance. So far, so good. So this is basically two capacitance in series. If this is the complete story, then, well, it's not that exciting. We find another nonlinear capacitor, but we already have one with the reverse bias, the PN junction. So what's the big deal? So the big deal is actually something magical happens on the positive voltage side, okay? So this is kind of a summary of everything on the MOS capacitor. We already discussed the very negative voltage. So this is the region we call accumulation. Okay, and we have this kind of 1 over square root type of dependence with voltage. This is area we call depletion. Okay, so think about reverse bias is depletion. Somewhere here above VT, VT is threshold. When it's above threshold, well, what happened? It really reverted back to that parallel plate capacitor. When we apply a voltage here that are really VG, that are much, much greater than that threshold voltage VT, so it wants to behave like a parallel capacitor where it will induce a lot of electrons in this area. But in the depletion, before we enter that area, well, nobody can supply that electron. This is a p-doped substrate. We have plenty of holes everywhere, but we don't have supply of electrons. So if we build two contact, if we build two contact with N plus doping, N plus means heavy N-type doping. So if we introduce these two additional N-type semiconductor, well, it's like a PN junction here, but these N-type semiconductor can supply holes. So when we are above that threshold, the potential energy is such that it's favorable for the electron to occupy the interface adjacent to the oxide. So now we have a sheet of electrons here, okay? So this sheet of electrons induced by the gate voltage. So this make them behave like parallel plate capacitor again. And capacitance is again equal to the oxide capacitance. Okay, so you'll see brief, very sharp snapping back of the capacitance value back equal to Cox. Okay, this region we call inversion region. Again, these are standard terminology for MOS. Everybody use the same terminology. Why inversion? Because this is a p-type substrate, but we have created a mobile electrons there. It's an invert of the doping type, so it's called the inversion. We refer to this sheet of electrons as the inversion inversion sheet or inversion channel. So later on, when we talk about the transistor, we will be referring to this sheet of electron as a channel. We will call that a channel. Okay, so this is new. This inversion, okay, so this inversion, this is the new part. This is what we have not discussed before. And this does not exist. This doesn't have an energy of the PN junction. In the reverse bias PN junction, doesn't matter how hard you reverse bias it. There's no inversion like this. You need the oxide there to provide a barrier for that electron to stay at that interface. And you need a place for the electron to come from and out of when you are slushing the electron in and out. So you need these two contacts. So if you look carefully, this diagram kind of summarizes everything. For accumulation on the right, depletion in the middle, you only need MOS. You don't need that N plus doped region. But to see inversion, you do need that N plus region to supply source of electrons for you to move back and forth. So for this course, we're going to stay at this qualitative level. If you go to course like EE130, okay, they will go into detail all these flat band voltage below which is accumulation. There's an expression for flat band voltage. It's related to the doping type. It's related to what material you use for the gate, what material you use for oxide, thickness of oxide, and so on. And the threshold voltage, VT, threshold voltage, is also a well-defined value, okay? I won't ask you to memorize this expression. The whole purpose of including it here is just to show you the threshold voltage is dependent on the doping type, okay? It's dependent on the earlier flat band voltage. So the work function of different materials, which is material dependent, is dependent on doping here again, and this is related to doping as well. So it's a voltage that we can design, and in a transistor, they are also very carefully controlled. Later on, we will see all your transistor characteristics depends on this threshold voltage. In order to have uniform threshold voltage, in order to have uniform circuits, if you have an IC with 10 billion transistors, if each one of them have a fluctuation of this threshold voltage, well, it's impossible to have integrated circuit work. So just the fact we can integrate that many transistors suggests we have very precise control of these threshold voltage. It is engineering feast as a result of decades of engineering effort. This really needs we precisely control the dopant, the doping depth, doping type, uniformity across 12-inch wafer when you do the processing. When you put down the gate oxide, it's uniform to within basically one atomic layer across that 12-inch wafer. This is the level of control that's enable us to enjoy all these nice features you are using on your phones. This is a very powerful ICs, has lots and lots of these devices in there. Questions so far? You have already started doing your lab, so I don't want to cover too much of MOS FETs. Usually, I think before the midterm, many people, their brain stops taking new knowledge. Have to wait until after the midterm. So I'm just going to mention something that may be helpful for your lab. Okay, so we'll skip some of the material. Don't worry about that. We will come back to these materials. But I want to talk about these variable conductance here. So this is the picture like a MOS capacitor we just mentioned. So when the voltage is VGS is greater than the threshold voltage, greater than VT, okay, we enter this inversion region. So we enter the inversion. And inversion means now I have a channel between my two other terminals. If I call this terminal source, because it's a source of electron, I call this terminal drain because it's draining electrons, okay? In between, I have, by applying gate voltage, I have channel. This channel is basically, channel consists of electrons. I have an N plus doped source. I have an N plus doped drain. I have electron, which is negative type. This means it will conduct current. If I apply a voltage to the drain, and I will have current flowing in this in between source and drain. So this is the current that you are using in deriving this variable amplifier that you are constructing in your lab right now, lab 3. How do you think about these? How do you estimate this current? Okay, so estimate current. Let me add a page here. So to estimate the current, let me exaggerate the channel, okay? So this is my channel. And here is my N plus. So here is my source, okay? And here is again N plus, here is my drain, okay? But in between, this is the equivalent resistor that we want to estimate, okay? So for channel, let's assume the thickness is a T channel, okay? The width is W, okay? And the length is L, okay? What is a current? Well, we learned current, J, is equal to conductance times electric field. And the conductance we learned should be NQ mu N, right? That's a sigma times a voltage. Electric field is basically equal to VDS. Let me use small VDS. VDS divided by L. So voltage drop across channel. If I apply, so this side, I will apply VDS. And this side, I ground it. Okay, so that's basically the equation. The current is going to flow in, the electron go to the right, current flow to the left. I'm not going to keep track of current. So I'll just put down VDS divided by L, okay. What is N? Well, N, we can estimate, N is a carrier concentration, okay. So from voltage, from capacitor, we know the charge, okay, charge is equal to, so Q is equal to CV, okay. And what is V here? Now this is different V. This is the gate voltage. So this is equal to C aux times VGS minus VT. So this is the voltage at the onset after we start forming the channel, after we start have inversion. If they are equal to 0, there's no charge. If VGS equal VT, there's no charge. So once I surpass the threshold voltage, I start to accumulate electrons. This Q here, in the semiconductor terminology, all these are per unit area. Okay, so I really need to multiply by the area, which is W times L. So this is the area. Okay, then I have a total charge Q here. Okay, so this is coming from MOS capacitor. This charge comes from MOS capacitor in the inversion region. Okay, so derivation is very simple. So N is therefore equal to Q divided by the volume. What is volume? W times L times thickness of the channel. Okay. And what we are really interested is current, IDS. Okay, IDS is equal to J times cross-sectional area. It is this cross-sectional area that we are multiplying since current flows horizontally. So J times T channel times W. Right, so I'm converting current density to total current. And the rest is just a substitution, okay? So, so J is equal to NQ mu N times VDS divided by L, and I'm going to multiply by T channel times W. Next, I substitute into N. N is equal to Q. Q is this value, Cox times VGS minus VT times W times L, and divided by W divided by L times T CH. Okay, so this is N. So this whole expression is N, and times Q times mu N times TCH times W. Okay, so let's see, quite a few things can be canceled out. TCH cancels out, W cancels out here, okay, and L cancels out. Oh, I haven't finished the original expression. It's J times NQ mu, NQ mu times area. Actually, I left out the voltage. So V ds divided by L. Yeah, that's everything. Okay, so this is what you need in your pre-lab. So my total current, actually, it doesn't matter here, it's only DC. So my total current, IDS, is equal to what's left? Mu N, okay, I have mu N Cox, mu N Cox. I'm writing it in notation that's easy to keep track of. And I have Q here, and I have VGS minus VT, and I have W over L, I have VDS. Okay, so basically the equivalent resistance at this particular bias condition is, if we call this R channel, okay, it is equal to VDS divided by IDS, okay? So that's equal to 1 mu N Cox. Actually, there's no Q, so my apology. Q is already in capacitance, so no Q, thank you. No Q here, no Q here. Yeah, thank you. Indeed, it's already in Cox. And what else do we have left? We have VGS minus VT, and we have W over L. Okay. So W over L is geometry. Okay. This is how wide you design your transistor to be. So these are geometric dimensions. This is your gate bias. So this is your gate bias. You can control. This is something you can control by just applying voltage. Mu n is electron mobility, Cox. Once you chose a technology, the oxide thickness is fixed. So it's automatically fixed parameter. So it's a variable resistor. How do you vary it? You choose the right order of magnitude. If you are laying out the transistor, you choose W and L. As an IC designer, you do have flexibility to choose W and L. As a user of this transistor, you can vary VGS. So it's a linearly variable resistor, or an inverse linearly variable resistor. And when you apply that to your op-amp circuit, you can control, if you use it in an inverting amplifier or non-inverting amplifier, you can now vary your gain. Question?
What happens if VGS is less than VT?
Then basically it goes to 0, and you can see, well, these channel resistance go to infinity. So 0 current flow. For now, let's say 0 current flow. As we finish the discussing of the MOS, we will come back and look at what happened when V is smaller than threshold voltage. One of the key problem of the future scaling of transistor is they don't really skyrocket to 0. They don't drop to 0. They drop very slowly, and that's a problem. For now, think about it just cut off. It just transistor is cut off, no current flow. Question in the back?
Yeah.
Threshold voltage. Short answer by taking 130, EE130. Long answer, so let's get back to my last view graph here. This is a threshold voltage expression. And you see what is related to. It's related to NA, so acceptor doping of the body part. And here NA appears again. And Cox, so it's related to the thickness of the oxide. So, you know, all these physical parameters. Exactly how these come from, we won't have time in this course. So EE130, you'll find out very precisely all the physics behind this threshold voltage. So here we are treating it as a parameter. Once you select the technology, let's say you are designing in TSMC 16 nanometer node devices, then this is all fixed. Okay, all right. So please practice on the homework and sample midterms. Thursday will be dedicated to answer your questions. Okay, see you on Thursday.